Welcome to new session on mathematical modeling, quantitative differential equations. Analytical methods. In this section, we consider models that lead to differential equations that have explicit solutions. Here, the examples were chosen to illustrate a variety of models, not to illustrate methods for solving differential equations. Industrialist nations are beginning to face the problems of water pollution. Once pollution of a river is stopped, the river will clean itself fairly rapidly if the pollution has not caused extreme damage. Lakes present a problem because a polluted lake contains a considerable amount of water which must somehow be cleaned. The only presently feasible method is to rely on natural process. How long does this take? In particular, how long would it take to clean up the Great Lakes? Pollution affects a lake in many complex ways. Some compounds such as DDT enter biological systems and move up the food chain. Since DDT is very soluble in fat, it concentrates the fatty tissue of higher predators and is hard to remove from the biosphere. Some pollutants move rather freely in and out of the food chain. The behavior of phosphorus lies somewhere between these two extremes. In one sense, phosphorus is not a pollutant since it occurs naturally. However, excessive amounts can trigger alga blooms and it is then considered a pollutant. Still, other pollutants like oil spills may be only slightly involved in the food chain. Extensive pollution can cause irreversible damage and even kill a lake. The main cleanup mechanism is the relatively straightforward natural process of gradually replacing the water in the lake. In addition, other processes such as sedimentation and decay may be important. If we consider all these facets of problem now, the discussion will go on and the resulting model will probably be hopeless. Long chain polymers. Our booming synthetic fabric industry relies on chemical reactions that produce long chain organic polymers. Thus, important to understand the nature, speed and end products of polymerization reactions. We study one type of reaction here and another in problem 3. The material is adapted from C. Tanford 1961 chapter 9. We need some background in chemistry. A simple reaction of the type we wish to study is given in the figure, where n greater than or equal to 0 and the radical R dash provides the mechanism for the reaction by breaking open the anhydride ring. We write the reaction symbolically as A plus Mn implies Mn plus 1 plus CO2. The compound Mn is called a polymer of length n for fixed temperature and pressure. The rate of a chemical reaction like equation 1 depends on the probability of a collision between a molecule and an Mn molecule. This is proportional to the product of their concentration, which is written as concentration of A into concentration of Mn. Thus, the rate of reaction of equation 1 is Kn into concentration of A into concentration of Mn, where the rate constant Kn is practically the same for all n. A typical process starts with a concentration A naught of capital A and a concentration M00 of M naught, which is simply R dash H. How does the system evolve? To begin, since the concentration of R dash does not change, we have the conservation equation summation n equal to 0 to infinity Mn of t is equal to M0 of 0, where Mn of t is concentration of Mn at time t. From equation 1, we have dm naught by dt is equal to k into A of t m naught of t. dmn by dt is equal to k into A of t into mn minus 1 of t minus mn of t, where n greater than or equal to 1. dat by dt is equal to minus k into A of t into summation n equal to 0 to infinity m into n of t. Combining second and third C, we obtain dat by dt is equal to minus k into m0 of 0 into A of t, which has the solution A of t is equal to A of 0 into e power minus lambda t, where lambda is equal to k into m naught of 0. We can simplify equation 3a and 3b by defining a variable y such that dy is equal to k into A of t into dt, y is equal to 0 at t equal to 0. For equation 3a and 3b, then can be written as d m naught of y by dy is equal to minus m naught of y, d m n y by dy is equal to m n minus 1 of y minus m n of y. These equations are easily solved inductively to obtain m n of y by m naught of 0 is equal to e power minus y into y power n by n, a Poisson distribution with parameter y. Thus, the mean chain length is y and the variance of the length is also y. We now use equation 4a and 4b to determine y as a function of t. Y of t is equal to integral 0 to t k into a0 into e power lambda t dt, which is equal to a0 by m naught of 0 into 1 minus e power minus lambda t. How can we produce polymers of some desired length L? Setting y is equal to L, we obtain t is equal to minus log 1 minus m naught of 0 into L by a naught by k into m naught of 0. Since the Poisson distribution can be approximated by a normal distribution, when y is large, about 95% of the lengths lies between L minus root L and L plus root L. Note that altering reaction run and has no effect on the distribution of final chain lengths. Let us examine briefly what happens if we relax the assumption that k power n is equal to k. If k power n is a decreasing function of n, the reaction proceeds more slowly than expected as time goes on, because the polymers are becoming longer. Also, the final distribution of chain lengths is more peaked than a Poisson distribution, because the shorter chains increase in length faster than the longer chains. You should be able to explain what happens when k n is an increasing function of n. How can we use these results in chemical engineering? We can use equation 7 to determine the optimum values for m naught of 0 and a 0. To make the reaction run as fast as possible, both m naught of 0 and a 0 should be large. Since there is an upper limit to the possible combined concentration of capital A and m naught, only so much will fit in a given volume. We obtain an inequality 0 less than or equal to a naught less than or equal to f m naught of 0, where f dash less than 0. As already noted, the larger r is equal to a 0 by m naught of 0 is, the faster the reaction proceeds. Since fast reactions save time, increasing r increases the number of batches we can process. Unfortunately, when we stop the reaction A, remaining will be alpha is equal to m naught of 0 into r minus 1. Thus, if we cannot reclaim the remaining capital A, or if reclamation expense increases with the quantity, a larger will increase our expenses. By studying the details of paid operation, we can construct a cost function depending on T, A, m naught of 0 and R, where T and A are given by equation 7 and equation 9. We can then minimize this subject to equation 8. In this way, it is possible to reduce cost considerably over what they might be for a naive approach to plan design. Numerical methods. In this section, we are not concerned with how the actual numerical solution of a problem is carried out, but rather with models that lead to a need for numerical solutions. A variety of numerical one package for solving differential equation numerically. Towing a water skier. You may have noticed that a water skier tends to slow down when the boat towing him turns. Two factors influence this. First one, for the same amount of power, a turning boat travels slower than a boat moving on a straight course, and second, the skier tends to follow a shorter path than the boat. Can we model the situation? Let us look at the skier first. If he drops the tow rope, he will lose speed very rapidly because of the drag of the water. Thus, the skier always moves practically along the line of the tow rope unless he can do something to affect his direction of motion. He can exert some control through the position in which he holds his skis in the water. To avoid this rather grave complication, we assume that the skier does the easiest thing and keeps his skis pointed toward the boat. Thus, we have created a skier whose rope is always taut because of the drag of the water and who always moves in the direction of the rope. Let the tow rope length be L, the coordinates of the rear of the boat be x of t, y of t, and the coordinates of the skier be r of t, s of t. By considering the length of the rope and the direction of the motion of the skier, we obtain two separate equations. L square is equal to r minus x whole square plus s minus y whole square. S dash t by r dash t is equal to s minus y by r minus x. We manipulate these two equations to obtain a set of two first order equation for r t and s t. By differentiating equation 1a with respect to t, clearing fractions in 1b and rearranging each of them, we obtain two equations in r dash and s dash. 2 into r minus x into r dash plus 2 into s minus y into s dash is equal to 2 into r minus x into s plus 2 into s minus y into y double dash. Then s minus y into r dash plus r minus x into s dash is equal to 0. Solving for r and s and using equation 1a, we obtain r dash is equal to x dash into r minus x all square plus y dash into r minus x into s minus y all divided by L square, and s dash is equal to y dash into s minus y all square plus x dash into r minus x into s minus y whole divided by L square. Before we can solve equation 3, we must mod the motion of the boat. Knowing the boat's course is enough to let us determine the skier's course. If we know y as a function of x, multiplying equation 3 by dt by dx gives a set of two differential equations which can be solved numerically for r and s as a function of x. This gives us the path of the skier parametrically in terms of x. We now determine his speed in terms of the boat's speed v. The component of the boat's velocity is v by root of 1 plus y dash x whole square by basic calculus and geometry. Thus, the square speed is root of r dash x square plus s dash x square into x dash of t is equal to root of r dash x square plus s dash of x square into x dash of t, which is equal to v into root of r x plus s dash of x all square divided by 1 plus y dash x square. Hence, the square speed at any time equals the board's speed at that time multiplied by some function of the paths of the square and the board. Alternatively, we can solve equation 3 under the assumption that the board speed always equals 1. We will obtain the path of the square and by the argument just given, a speed for the square which is equal to the square's true speed divided by the board's true speed. This enables us to treat the problem of the board's speed as a completely separate issue. Since it is complicated hydrodynamic problem, we do not attempt to solve it. Consequently, we obtain only a partial solution to the problem we started out with. However, the full solution will be easy to find if and when we obtain information on the speed of a speedboat making a turn. We could try all sorts of paths for a turn. The simplest to program is a circular arc and this is a reasonable path. By defining x of t into b into L cos t by b into L and y of t into b into L cos t by b L, I obtained a circular course with radius equal to b rope lengths and a speed of 1. It would be interesting to note how far the angle of the rope deviated from a line straight back from the board. By substituting equation 4 into equation 3 and integrating numerically, found that with b equal to 1, a very sharp turn, the speed of the square dropped markedly. After a 90-degree turn by the board, his speed was 67% of the board's and his angle with the line of the board was 47 degree. After a full 180-degree turn, the figures were 45% and 63 degree. By the time the radius of the turn was twice the taut rope length, the situation had improved considerably. The square speed was still 86% of the board's speed after a 180-degree turn and his angle was only 30 degree. The changes were fastest at the start of the turn. In fact, after 45 degree, the square speed had already dropped to 92% and his angle was 23 degree. With a turn of radius 4 times the tow rope length, the speed change was negligible, still 96% of the board speed after 180 degree. The tow rope's angle with the line of the board was only 14 degree. The lesson is quite clear. To keep up a water skier speed, be sure the radius of your turn is at least twice the top rope length. A radius 4 or more times the tow rope length result in almost no loss in the speed of the skier except for possible loss due to the boat slowing in the turn. Alternatively, the skier can maintain his speed by pointing his skis somewhat outward from the direction of the turn, so that he does not move in the direction of the rope. The analysis of this situation appears complicated. We seem to have completed the problem. This was reaction until when examine the data a bit more closely. Look at the data. B equal to 1, theta is equal to 0 degree, phi equal to 0 degree and W is equal to 1. B equal to 2, phi is equal to 0 degree, W is equal to 1. B is equal to 4, phi is equal to 0 degree, W is equal to 1 and so on. It is reproduced here. the angle the boat has turned through is theta. The water skier's angle with the boat is phi and his speed divided by the boat's is w. Incidentally, finding the formula for phi is a non-trivial problem. You should do it. Note that w appears to depend only on phi. Let us prove this for any motion and compute the function w of phi. For simplicity, we move the co-coordinate system so that at t is equal to 0, the boat is at the origin and its direction of motion is along the x axis. Hence, we have at t is equal to 0, x equal to y equal to 0, x dash is equal to 1, cos phi is equal to minus r by t, w square is equal to dr by dt all square plus ds by dt all square. By equation 3, r dash is equal to r square by l square and s dash is equal to r into s by l square. Hence, w square is equal to r power 4 r square s square by l power 4, which is equal to r square by l square, and so w is equal to cos phi. Such a simple formula is unlikely to depend on more than a simple geometric argument. Can you find one? A ballistics problem. During World War II, mathematicians were asked to construct tables for gunners relating angle to range. Bombardiers required similar information. How was this done? In this case, the model is fairly straightforward and the emphasis is on the mathematics, in contrast to most other models we have studied. We wish to construct a model of the motion of the object under the influence of gravity and air resistance. This material is adapted from T.V. Carman and M.A. Bayot 1940, paper 139 to 143. We ignore the complications due to lifting forces and possible rotation of the object. Hence, the only forces involved are a downward force of m into g and drag force opposite to the direction of motion of m into f of v, where m is the mass of the object and v is equal to modulus of v is the magnitude of its velocity and g is the acceleration due to gravity. In the xy coordinate system with the positive y axis directed downward, we can write this as a vector equation. V dash is equal to 0 g minus f of v by v whole the power v. Over a fairly large practical range, f of v is nearly proportional to v square. Let theta be the angle between v and the x axis and resolve the acceleration into components parallel and perpendicular to v. To do this, we need to know values of v dash in the two directions. Since v is equal to v cos theta, v sin theta, v dash is equal to cos theta, sin theta, v dash plus minus v sin theta, v cos theta into theta dash. The parallel component is simply v dash and the perpendicular component is v into theta dash. Resolving the acceleration due to gravity into components parallel and perpendicular to v and using the fact that drag acts parallel to v, we obtained v dash is equal to g into sin theta minus f of v, v theta dash is equal to g into cos theta, multiplying equation 1a by v g cos theta dividing by 1b and rearranging, we obtain g into d of v cos theta by d theta, which is equal to minus v into f of v, an equation we cannot solve analytically unless f has some special form. If we assume that f of v is equal to k v square, we obtain g into d v x by v x cube is equal to minus k into d theta by cos cube theta, where v x equal to v cos theta, the component of v in the x direction. Hence, v x minus 2 is equal to 2k by g integral cos power minus 3 theta d theta. Suppose that v is equal to v naught comma 0 when theta is equal to 0, carrying out the integration and rearranging, Vx equal to r of theta, Vy is equal to r of theta into tan theta and V is equal to r theta by cos theta, where r 0 is equal to V naught into 1 plus k into V naught square by g sin theta by cos square theta plus log of 1 plus sin theta by cos theta to the power minus 1 by 2. We now integrate these velocity equations to obtain the path of the object. Let the origin be at theta equal to 0. Using in succession the chain rule, Vx equal to V cos theta and we have dx by d theta is equal to Vx by theta dash, which is equal to V cos theta by g cos theta by V, which is equal to V square by g. Similarly, dy by d theta is equal to Vy by theta dash, which is equal to V sin theta by g cos theta by V, which is equal to V square tan theta by g. Combining equation 2a with 3 and 4, we obtain the coordinates parametrically in terms of theta, that is x of theta comma y of theta is equal to integral r theta square into d theta by g cos square theta integral r theta square sin theta by g cos cube theta into d theta. Since r theta is given by equation 2b, the integration in 5 can be carried out numerically. An alternative approach is solve the original differential equations directly by numerical methods. This is more sensitive to numerical errors because the original equations are linked second order equations, while equation 5 simply involves two disjoint integrals. We can supplement equation 5 by obtaining time information using equation 2a to eliminate v in 1b, r theta into theta dash is equal to g into cos square theta. Thus, t is equal to integral r theta d theta by g cos square theta. Since our time origin is at theta is equal to 0, we must integrate back from 0 in equation 5 and 6 to obtain the initial position for a projectile fired upward. Now, let us summarize what we have discussed so far. In this section, we consider models that lead to differential equations that have explicit solutions. Here, the examples were chosen to illustrate a variety of models, not to illustrate methods for solving differential equations. Our booming synthetic fabric industry relies on chemical reaction that produce long chain organic polymers. Thus, it is important to understand the nature, speed and end products of polymerization reactions. We studied one type of reaction. In towing water skier, we are not concerned with how the actual numerical solution of a problem is carried out, but rather with models that lead to a need for numerical solutions. A variety of numerical methods exist in literature and most computing centers have at least one package for solving differential equation numerically. Here are some problems to work out. First problem, can we construct a simple model of the spread of epidemics? We take as our example measles, a prevalent childhood disease before vaccinations became available. The incubation time is 1 week. During this time, a child seems normal but is able to infect others. After this time, the child is isolated until recovery, at which point he or she is immune. Roughly speaking, measles outbreaks have been more severe during alternate years. First one, construct a simple differential equation model allowing for 3 categories: susceptible, infective and isolated recovered. Allow for an influx of new susceptibles due to births. Assume an infective makes contact with the members of the population at random and infects a contacted susceptible with the probability p. Second question, construct a simple difference equation models. Problem 2, give an account of ballistics problem. Problem 3, consider a reaction of the form Mk plus Mn goes to Mk plus N plus H2O. Study the concentration of Mn of T. Problem 4, at what age are your friends going to be marrying most rapidly? 15, 20, 25 or 30. What factors cause people to marry? Sociologists and psychologists generally believe that peer group behavior plays a major role. Can we model this? It is assumed that a person's chances of marrying in some small time interval delta t are proportional to delta t and to the fraction of the people in the person's age group that are already married mt. This is based on the idea that there is overt and covert peer group pressure to marry. Show that this leads to the differential equation m dash is equal to c into m into 1 minus m. Solve the equations. For further reading, you can refer An Introduction to Mathematical Modeling by Edward A. Benter, Wiley InterScience publication 1978. Concepts of Mathematical Modeling by Walter J. Mayer, Dover Publications 1984. Mathematical Modeling, Classroom Notes in Applied Mathematics, edited by Murray S. Clamkin, Swayam Publication 1995. Differential Equation Models, Volume 1, edited by Martin Braun, C. S. Coleman, D. A. Drew. A Concrete Approach to Mathematical Modeling, Mike Masterton Gibbons, Wiley InterScience Publication 1995. Hope you followed this session clearly. See you next time. Until then, goodbye.